Welcome everybody to today's webinar presentation. I appreciate everyone's time today and joining us. Pretty excited personally about the material that is going to be discussed today. It's a little bit of some stuff that I think we all know, but coupled with a lot of new things that I think are going to change how you think about applying, especially EVO to your sites for bio. Okay, so real quick, as there's still a lot of people, I can see it on the screen on my end. There are a lot of people very quickly trying to rush in here before we really get going with the presentation. So while everyone is getting logged in, let's just do a few housekeeping items. I guess number one is just a quick sound check. As these things tend to go, technology sometimes fails us. And if you look in your dashboard on the GoToWebinar screen, you'll actually see a little box that says questions. And that's where you can type questions that at the end of the webinar, I will read to Dr. Borden and he will answer. But for right now, just to do a sound check, if a few people wouldn't mind volunteering and just giving me a question that says, yes, you can hear us and everything's coming through loud and clear, that would be great. Also, if you do lose audio during the webinar, this has happened a few times in the past, and a quick fix is if you're listening to us through speakers, through your computer audio, close all that out, mute all that, and then dial in with your telephone. The telephone always seems to be the most secure way to listen to stuff. So if that does happen to you, try muting your speakers and picking up the telephone and dialing in. And if you still don't have any luck, you send me a question and I can do what I can from here. Awesome. I got a whole bunch of wonderful volunteers, so everybody can hear me. That's good. Great. And so now that you know how to use the question box, now you also know how to use questions. So we just killed two birds with one stone. All right. Everybody is muted for everyone's benefit. So at the end, we will just take questions. And of course, we will do it, like I said, in that box there. For those of you, I think I looked at the registration list. I think pretty much everyone that's listening in has at some point engaged us. Whether you've purchased some product from us or you've just inquired about some things. I think everyone's pretty familiar with who EOS is, but just in case this is being broadcasted to a bigger audience, maybe at your office, or eventually we will make this recording available. So if you don't know who EOS is or what we're about, so EOS Remediation, we've really earned recognition in the industry as experts in the field of in situ remediation. And we literally wrote the book on how to use emulsified oil for treating chlorinated solvents. And I'm referring to our AFC and ESTCP protocols that you can Google on the web and find and download and read for yourself. So 15 years later, we've been in business since 2002. Over 15 years later, we're still maintaining our industry-leading status in the remediation world. We've developed further products. We've continued to enhance current products that we offer. We offer customization on products. Should something that we have off the shelf not meet your spec, we can customize a solution for you. And then I take great pride in trying to provide personalized project assistance to each and every one of you. My goal each and every time is to exceed your expectations. And so if we ever don't do that, please give me that feedback. It's the only way we will get better. So today I'm pleased to present or introduce Dr. Robert Borden. He was formerly an engineering professor at North Carolina State University. He's the inventor of the EOS technology. And today he is going to be presenting how to improve bioremediation performance, which is going to cover some of his most recent research he has done through CERTUP and ESTCP. And Bob, if you are able, you can go ahead and chime in and get started.
Hi, Brad. Can you hear me?
I can hear you loud and clear.
All right. So are you going to turn over to me, or have you already turned over to me? Or
I'm going to do that now.
Okay. Hello, everyone. As Brad said, my name's Bob Borden. I've been working on this subject for a while. And what I want to share with you today is really well, two things. One, some stuff we did years ago when we originally developed the process, but really what's motivated this is I recently completed a couple projects funded by ESTCP and CERTIP, where we went back and looked at some old sites and, well, found some things out that I don't think are totally surprising, but, well, they're, unless you look at them again, you sometimes you don't know. So I'm going to get started. Okay, so when I say first improving bioremediation performance, what I'm really talking about is anaerobic bioremediation of chlorinated solvents, enhanced reductive dechlorination with emulsified vegetable oil. Yeah, I'll get started. If someone's, maybe you should mute your mic or something because I can hear some feedback. Okay, so emulsified oil process. Very, very brief review. Go out, you install temporary and permanent injection wells. You get emulsion, you dilute it with water, you inject it, the oil droplets flow out through the formation, they eventually stick to the sediment surfaces, the oil slowly ferments to hydrogen and acetate, and then that hydrogen and acetate drives the biodegradation process. Now that's strictly focused on treatment with vegetable oil. You can obviously add soluble substrates, you can add buffers, you can add nutrients, you can add specialized bacterial cultures that all further this process. But that's the EVO process is really what I'm talking about right now. Okay, this is results of what I'm showing you here is order of magnitude declines in parent compound concentration, and it's results from two studies. One by Travis McGuire at GSI. He had a series of CERTA projects where they went out and they basically collected data from a bunch of sites and looked at what kind of removal efficiency people were getting. And I went into his database and I basically just extracted out 19 sites where they use slow release substrates. Not necessarily EOs, it could be other slow release compounds, but slow release. And he reported it two different ways. One, changes in the geometric mean concentration of all the wells on the site. And then also, when I showed 19 site maximum, that's essentially the dirtiest well on the site and what removal efficiencies they got for that. The 184 wells, that's results of a study that Jason Tillison and I did, I guess it was published last year, where again, we went out to a bunch of anaerobic biosites. The 184 wells is not just EVO, that could also be soluble substrates, but EVO is really the most common substrate, so it's most of the data in those 184 wells. And what this shows you is in the box and whisker plots is that, kind of on average, most sites are getting about a 1 log unit reduction in parent compound concentration on average. Sometimes it's a little less, sometimes actually it's a lot more, and sometimes 2 orders of magnitude reduction or even 3. And I think generally people think, based on this kind of data, that anaerobic bio with emulsified vegetable oil is a pretty good, robust, reliable technology. You really don't see much better removals with almost any other technology. That said, well, there's some of these sites here where you see 3 and 4 log unit reductions, and I'm kind of a the glass is half empty person. I always want it to be better. So even though we're getting 1 log unit reduction, I'd like it to be 2 or 3 log unit reductions. And that's what I mean by improved performance. Well, in the Travis McGuire study, he only looked at parent compound. Well, we went back, and in addition to parent compound, we looked at daughter products. And what I'm showing here is just the the wells with TCE as the parent compound. And as you can see, the red box on the left, that's parent compound removal. And again, it's the same basic results where you've got about a 1 log unit reduction in TCE concentration. On average, some higher, some lower. But then you look at DCE, and actually on average for these sites, there was 0 net removal of DCE. We were making as much DCE as we were degrading. So 0 log units is basically no change in concentration. Vinyl chloride concentration actually went up. So it's showing a negative vinyl chloride concentration removal of about a half a log unit. Well, as we were working on this project, we were sort of stymied by, well, okay, TCE went down, but vinyl chloride went up. Was that a good thing or a bad thing? And so we came up with this measure called sum of chlorine. And what that is essentially the moles of organic chlorine present in chlorinated ethynes present in the groundwater. And so that would be sum of organic chlorine would be 4 times the molar concentration of PCE plus 3 times TCE plus 2 times DCE plus 1 times vinyl chloride. And essentially, if you want a clean site, you have to get all of the chlorinated species gone, or you have to get the sum of organic chlorine to 0. And so we like that as sort of an integrated measure, even if you're doing a great job on TCE. If you're not doing a good job on DCE, you won't get that high sum of organic chlorine. And so you can see the sum of organic chlorine is, the mean is about a half a log unit. Not bad, but we'd like it to be better. And so we went around and went to several sites, did some fairly detailed investigations, and basically tried to figure out why we weren't getting better removal. Most of what I'm going to show you is the results of an ESTCP project we recently completed, titled Post-Remediation Evaluation of EVO Treatment, How Can We Improve Performance? And the basic lessons we found was that PCE and TCE, we were getting excellent removal of parent compounds. Often at the sites we looked at, significantly better than that 1 log unit, a lot of times 2, 3, and even 4 log unit reductions in TCE. And it wasn't that DCE wasn't getting converted to vinyl chloride and ethene. It was. No, we were getting significant ethene production. The problem was it was just TCE was degrading a lot faster than DCE was getting reduced. So at least the way I looked at it was DCE degradation was the rate limiting step in the process. Not that DCE wasn't going away, it just wasn't going away quite fast enough. And so what we were trying to do is figure out, well why? We looked at the halicoides counts. That was not the cause. Pretty much all the sites I'm not saying that DHC was not naturally present, but if it wasn't present, we bio-augmented, and so we had good bugs. There were a number of wells where we had a pH less than 6, and that was inhibiting DCE and vinyl chloride degradation. That was definitely a problem, but that's not really the focus of this presentation. I'm going to be talking mostly about EVO distribution, and we'll talk about pH and how to buffer aquifers in a future webinar. So what I really got to was that it's not that we didn't provide an EVO and that we didn't get good treatment at some areas. We just did not get good treatment at every area. And if you want to clean up a site, you can't just clean up 90% of it. You have to clean up all of it. So, okay. So give you a little background on why we think this was an issue. Okay, soybean oil is basically composed of a triglyceride. That's that picture in the upper right-hand corner, which is really one glycerol with 3 long-chain fatty acids attached to it. When you add the soybean oil to subsurface, the long-chain fatty acids get cleaved off. Both the fatty acids and the glycerol get fermented to hydrogen and acetate. Now, to degrade PCE and TCE, the bugs that do that are fairly common, and they can use both hydrogen and acetate. However, to degrade DCE and vinyl chloride, you need dihalococoides, and dihalococoides can only use hydrogen. Well, it turns out that in the subsurface, hydrogen turns over very, very, very rapidly. So, really, there's only a hydrogen present very close to the location where the parent organic compounds are getting fermented. If you're, even 5–10 feet away, if there's carbon at one location, the hydrogen is not going to drift down the gradient. It's going to get consumed either by degrading TCE and vinyl chloride or by other electron acceptors. So, okay, now what are possible fermentation sources for hydrogen? Certainly, pretty much any place you have vegetable oil, it's going to be sorbed, and you're going to have a very good source of hydrogen. You can see that if you're at a location with vegetable oil stuck to the surface, you're going to see propionate, butyrate, valerate, these longer chain fatty acids, well, not long chain, but fatty acids, and they can ferment releasing hydrogen. Now the challenge is acetate does not ferment to hydrogen. So while acetate will drive TCE degradation, it won't drive DCE and vinyl chloride degradation. So you really need some of these higher molecular weight fatty acids. Here's some monitoring data from one of the sites. We went in and we sampled the injection wells, and then we also sampled 10 feet down gradient, not very far. If you look at the injection wells, a year out, we've got good levels of propionate and butyrate. Now, most of it's acetate. You can see that acetates increase steadily over time. But we've got definitely decent levels of propionic acid, and we can produce hydrogen at the injection well. As a result, TCE was non-detected in the injection well, but more to the point, DCE and vinyl chloride were very, very close to the detection limit, and it was 90+% ethene or 95% ethene. Just 10 feet down gradient, we had a monitor well. And while there was some soluble TOC there, if you look at the 10-foot down gradient graph, you can see it was mostly acetate. And after about 200 days, it was essentially all acetate. So we're now 10 feet down gradient. Conditions are very good for degrading TCE, but if you produce that DCE or vinyl chloride down gradient, there's no additional hydrogen being produced. So you're basically going to, it's not really stall, but you're just not going to get the good degradation rates for DCE that you hoped. The solution, if you have, particularly, I'm really talking about source areas here, if you have sorbed contaminant, you need to bring that oil really into very close, intimate contact with the contaminant, or at least as close and as intimate as you can possibly make it. Okay, so how do you improve EVO distribution? Well, this is really a lot of stuff we've done over the last 20 years. And so it's a little review, but I think some of you may not have seen it in a while. Heck, I haven't seen it in a while. This is kind of a review for me too. So, I'm going to talk about sort of EVO transport and some theory, as well as some some tips and tricks to try to improve contact. Okay, first thing I want to show you is some sandbox experiments we did like 20 years ago. And what you're seeing there is in the upper right hand corner here, this is sort of a plan view. We had basically a square box, at least on the top, with an injection well in the front left hand corner. And as you inject EVO in this corner, you'd expect it to flow out kind of radially. The figure I'm going to show you is what we did in both homogeneous sand tanks and heterogeneous sand tanks. I'm going to show you some photos of the heterogeneous one where the middle layer had the least fines, the top had the most, and the bottom had sort of intermediate amounts of fines. And when I say fines, that's silt and clay fraction. So this was all sand, but just the top and bottom layers have a little more silt and clay. Okay, there's our sandbox. It's sort of, I don't know, orangish brown dirt. You can't see it, but the injection well would be in the left-hand side of the box. There's a cap on top of bentonite. There's a cap on the bottom of bentonite, and there's a constant head boundary over here. So as we inject oil in the well here, it's going to kind of flow horizontally and discharge the tank over here. Here's a photograph of the sand tank kind of halfway through the experiment. What you can see here is that, well, it's kind of turned white and milky like EVO. And EVO spread the fastest in the middle sandier zone, and it's transported a little slower in the top and the bottom. And this is a picture of what happened after, at the end of it, after we stopped. We finished EVO injection, we flushed some water, and then we took a picture. And you can see, again, really pretty nice uniform distribution of EVO in this middle layer all the way through. But one of the things you can see is up here, like in the upper right-hand corner, this section, the aquifer, never got contacted by EVO. The permeability of the material here is lower, and the oil retention is higher, so it really didn't migrate that far. And based on that, we developed and tested a couple mathematical models. These are, well, the line is the model simulation results. The dots are the measured concentrations, and the net result of all this is close to the injection well, right 46 centimeters away. We got good distribution of EVO in all the layers, but now here about a meter away, we've got some EVO in the middle. I'm sorry, we'll quit that. We've got some EVO in the middle layer, but we really never got any breakthrough in the top or the bottom layers. And that's, well, not terribly surprising, but that's what it is. But I think that the key thing is, based on this modeling study, we feel like, if you know the permeability, if you know all those other things, we know how to make emulsified oil go where it needs to go. The trick is just mechanically doing it in the field. Okay, here's a little video of how we think oil transports. Just so you all understand, oil droplets typically are about a micron. If you've got sandy aquifer material, you're talking about pore spaces. They're in the order of 30 to hundreds of microns. So it's very easy for an oil droplet to migrate through the pores. The key really is over time, the oil droplets will sort of bump into the sediment surfaces. As I've shown here, the sediment surfaces often have a mixture of positive and negative charges. EOS is the oil droplets are negatively charged. So if it bumps into a negatively charged site, it's going to be repelled. But if it bumps into a positively charged site, it's going to stick. So really the amount of oil that gets retained is essentially a function of the number of positively charged sites. One way to measure that sort of the average electrical charge of the sediments is called zeta potential. And I'm going to show you some results of that in a minute. Okay, let's see, go on. All right, so how do we measure this maximum oil retention? Well, years ago, we developed a procedure. We basically take a laboratory column, we pack it with aquifer material, we pump oil, emulsified oil through it, we'll pump several pore volumes, and then we flush it with water, and then finally we take out the sediment. We measure the amount absorbed to the sediment by measuring organic carbon content, and we can get sort of this measure of maximum oil retention. That's not necessarily the amount that'll get retained in your aquifer, but it's sort of if you pumped oil through it continuously until you saturated all the sites, that's how much it would hold. And the reality is, near your injection well, oil is going to flow past that formation multiple times. And so near the injection well, the aquifer material really probably will be saturated with oil. Okay, no surprises, silts and clays hold more oil. They have more charged sites, and they just have more surface area. Depending on the surfactant you use, non-ionic surfactants typically have lower absorption, but that doesn't mean really low, it just means lower. Charged surfactants like lecithins tend to have much higher. And as I mentioned, the oil droplets are negatively charged, the clays tend to have a net negative charge, so it lowers retention. Okay, early on, I did a number of experiments where we measured oil retention in different materials, and you can see we got these numbers here, oil retention anywhere from maybe as low as 0.0004 grams per gram or pounds per pound to as high as maybe 0.01 pounds per pound, but generally fairly low. Well, that's the results we had from, well, I think, well, what's the oldest date here? The oldest date here was Mike Kovacic, 2007. So it's now been 10 years since then. And we really haven't published any more on this, but happily, Microbial Insights has been measuring oil retention for some clients. And what I've got shown here is maximum oil retention data measured by Microbial Insights. I got a big shout out thank that this has been really helpful. And it shows sort of a cumulative frequency distribution of oil retention. You can see here maybe the median is something less than 0.01, maybe 0.06 or 7. But there's a fair amount of data there above 0.01 grams per gram. That would 0.01 was really the maximum in that previous thing, and our early data was kind of in this range here. But you know, there's a decent number of sites here with quite a bit higher oil retention. And I can't say I really understand exactly why, but it certainly does seem like that. And if you have real high oil retention, you're going to get less effective distribution. We don't know completely why, but well, I'm going to share with you in a second some things that may help. One of the things we've come to realize is that the ionic strength of the groundwater can have a big impact on oil retention. What we did is, in the table at the right, you're seeing here, we measured zeta potential. That's sort of the electrical charge that's not a very scientific way to say it, but it's kind of average electrical charge on either the sediments or the eos. And you can see in DI water, the sediments at these two sites, SA17 and OU2, had charges of -29, -22, and -30 millivolts, and the EOS was -43. So, you know, I don't know, call that you know, maybe this is average -25, this is average -40. There's a fairly strong repulsion between the oil droplets and the sediments, so you don't get much sticking. And if you look at the bottom here, you see relatively low oil retention. Yeah, OU2 was a little higher, it's greater than 1, but it's, you know, still not that crazy. But now, when we flush this with 100 milligrams per liter calcium chloride solution, you see the zeta potential of the sediments is still negative, but it's much, much smaller. And the zeta potential of the EOS is much smaller, so there's much weaker repulsion. The reason why EOS doesn't flocculate is because one droplet has a negative charge, the other has a negative charge, and they sort of repel each other. Now that we've reduced the repulsion, it's much easier for one droplet to bump into another, and it's actually much easier for one droplet to bump into sediment too. And so, not surprising, you look down here, and the oil retention went up quite a bit. So what we found is that, well, higher total dissolved solids aquifers seem like they're going to have significantly higher oil retention. And I don't know how to fix that other than just it is. The other thing to be aware of is you can have high total dissolved solids associated with just the background groundwater of your site. But if you're adding salts, not lactic acid, but sodium lactate, or you're adding sodium bicarbonate, you know, a lot of aquifers are very, very strongly buffered. So if you need to raise the pH, you have to add a lot of buffer. Well, if you add a lot of buffer, you're going to increase the total dissolved solids concentration of your sediment, and you're going to get higher oil retention. That seems to be a fairly common thing. So if you're adding buffer, you really need to think about this and how you time the buffer addition. We've moved to injecting the EVO first, and then till you get the oil spread out, and then you add the buffer later. Since the oil's already spread out, the increase of the oil retention doesn't reduce or reduce distribution as badly. Okay, so we know this. So we've done some modeling studies. This is just a figure. We basically set up these models in the computer and try to figure out how to optimize injection. And what I'm showing you here is just sort of a hypothetical aquifer. The dark red are the high K zones, the light pink are the lower permeability zones. At the bottom shows the final oil distribution sort of in a slice. Now this is only injecting a little bit of oil. So this would be a relatively poor distribution, but I wanted to sort of show it as an example. And when you see, not surprisingly, where you have a high permeability zone here, you get a lot of spread in the oil distribution. Where you have a low K zone, it doesn't spread nearly as much. So we did a bunch of simulations trying to figure out how we could optimize distribution. And to sort of normalize this, we came up with two scaling factors. We have a volume scaling factor, which is just the volume of fluid injected, that's water plus EVO plus dilute EVO, just the total volume of fluid divided pore volume. So SFV is really the number of pore volumes injected. And SFM is the amount of oil injected divided by the maximum possible retention. So if you totally saturated every oil sediment surface with oil, you'd be at an SFF of M of 1. Now that would be very expensive because oil costs money, but that's what it would be. So we did some simulations, and I don't think you're going to find the results, you know, terribly shocking. But if you look at volume contact efficiency for a source area, as you inject volume scaling factor, this is the number of pore volumes injected. So for a constant amount of oil, as you go from 0 up to about 0.2 pore volumes of fluid, you get a giant increase in contact efficiency. And then it kind of plateaus out for a constant amount of oil. Yeah, you get some further improvement, but what this says is you really don't necessarily need to inject one whole pore volume. Maybe 0.2 to 0.4, 0.6 might be okay. But now this is for a relatively small amount of oil. I'll show you how they interact together in a moment. Similarly, for injecting 0.2 pore volumes of fluid, this is what the effective oil scaling factor is. And as you inject more oil, again, you get higher contact efficiencies. If you put those two together, you get this curve here. So for example, when I add a volume scaling factor, this curve here is a volume scaling factor of 0.2. So in this graph, the volume scaling factor of 0.2, this line here is essentially that curve I just showed you. So if you increase the amount of oil injected, it goes up a little bit, then it kind of plateaus, and it only goes up a little more. Versus if you start at 0.6 pore volumes injected, it goes up steeper and goes up higher. Even injecting an entire pore volume of water and the maximum amount of oil you need, you're only going to get, in a source area treatment for our simulations, a little less than, maybe 70% is the absolute maximum. But you can get to like 50%, with a lot less water and a lot less oil. So at least for me, when I design these systems, I'm aiming for kind of this area here. Maybe even a little bit over here. Injecting water is relatively cheap. Oil costs, EOs cost a fair amount of money. So I tend to inject a little bit more water and a little bit less oil to try to save money. Now that's for an area treatment. For a barrier, you can actually get quite a bit higher. Well, it's not volume contact efficiency, it's the amount of flow that gets contacted. And you can actually get very high flow contact efficiencies because, well, the contaminants flow to the high K zones. The EVO flows to the high K zones. So it's fairly easy to get the oil and the contaminant to mix and meet each other in a barrier. It's a lot harder in the source area where you have some low K zones that may hold contaminant, but they're very hard to get to. But again, here you see that same sort of rule where, as we're getting higher amounts of fluid injected, initially injecting more fluid has some benefit, but it kind of plateaus out here at maybe a half or 2/3 of a pore volume. And similarly, as you inject more oil, it increases contact efficiency, but it's sort of diminishing returns once you get over maybe 0.5, something like that. So that's the big controls you have on contact efficiency are the amount of oil you inject, the amount of water you inject. Now there's a third factor that I think people don't pay attention to enough is the sequence of the injection. And we've seen this sometimes, honestly, with our own guys, where they'll go out and they'll connect up all the wells in a certain area. So here I've got a simulation of the oil distribution if we in a barrier, if we simultaneously inject all these wells. Well, you see those, well, you think those little things should be circles, but they're not, they're kind of ovals. Well, if you're injecting water here, or EVO, it's going to flow radially out from the center in this direction and in this direction. And if you inject here, it's going to flow from here in this direction and in this direction. Well, if you simultaneously inject here and here at the same time, you've got a streamline going to the left, you got another one to the right, and right in between there's going to be a stagnation zone. It's going to be very difficult to treat this zone here because, well, the two water streams are sort of pushing against each other. Well, one way to solve that problem is don't inject all the wells at once, inject every other well. So I've got a second simulation where we inject this well, the well on the left, the middle, and the right at once, but we do not inject this well and we do not inject this well. Once that's finished, then we go back and inject this well and this well. And what you see here is pore volumes of fluid injected, contact efficiency for the same amount of oil. If you inject all the wells at once, you get a very rapid increase in contact efficiency, then it kind of plateaus out. Versus if you do every other well, what do you get? You get about 10% greater contact efficiency. And you didn't use any more wells, any more oil, and any more water. Your costs are virtually unchanged by those two different alternatives. Yeah, the field guys have to drag some more hoses around, and I got about a couple more hoses, but we've worked on this, and it's very small cost increase. Our basic procedure, what we'll typically do is we'll split the wells into two different groups. Group A is sort of every other well. We manifold all those wells together. We typically inject the EOs during the day. Try to finish up the dirty part of the injection by 3 or 4 in the afternoon. Then they can switch over. We tend to inject just plain water at night. I don't like to inject EOs at night when nobody's around. And then the next day we'll come back, we'll rearrange the hoses, and we'll inject the EVO during the day, and again, chase water at night. The advantage of this, one, that alternating approach eliminates stagnation zones. If we inject water at night, it saves some time. We can get in and out quicker. I really like to inject a lot of chase water, at least in permanent injection wells, because that moves the oil away from the well and reduces biofouling of the well. Now the disadvantage is if we inject at night, you spring a leak, we could have a big puddle of water out there. And we would never do this inside a building. But honestly, there have been a couple times when we've gone out there and it's sprung a leak and there's a puddle of water in the grassy area by the facility, and it was just plain tap water. At least for our site, it did not cause a problem. I won't advocate it won't cause a problem at your site, but you might think about it. It saves a little time and feel like that gets a better distribution. Okay, one of the last things I want to talk about is the PCB Design Tool. We developed this a few years ago, and I guess I'd really like people to take another look at it. I think it's got some big advantages. It's sort of like the EOS Design Tool, but it not only looks at just the amount of water and the amount of oil, but the spacing of the wells. And what you're going to find is that well spacing can have some significant impacts on costs. And we use the design tool, and we did this little case study. This would be for a permanent reactive barrier, hydraulic conductivity a little bit over 5 feet per day, depth of water 10 feet, saturated thickness of 30 feet, maximum oil retention of 0.04 grams per gram. That I would say now might be below average, and the barrier is 400 feet wide. We assume we're going to use 1-inch direct push wells, and we're going to inject a rate at 2 gallons per minute. And there's some of the costs you can see. The way it worked out is that you can see the lowest total cost is using a well spacing about 15 feet on center. If you get closer than that, your well space, you spend a lot of money on wells. If you spread it farther than that out, what you actually find is that it actually costs more for substrate and more for labor to use a wired well spacing. So the widest well spacing is not always the lowest cost. And it's pretty simple to run. I really encourage you to give it a try. Okay, so lessons learned. ERD with EVO is actually a pretty robust treatment technology. We've gone to some sites now that are 10, 15 years old, and honestly, we didn't know quite as much what we were doing 15 years ago. We look at it, we're getting pretty good removal. Orders, at least for parent compound, often we're seeing 2-3 orders of magnitude reductions in parent compound. However, daughter products are often not quite as good. A big issue we're going to talk about in a future webinar is low pH. But the other thing is that to degrade DCE and vinyl chloride, you need hydrogen. And that means you need some of the higher, more complex fatty acids, propionate, butyrate. Acetate does not produce hydrogen really effectively in the subsurface. And so if you've only got hydrogen at your location, you may not, if you only have acetate in a certain part of the aquifer, you're not going to be producing hydrogen, and you're not going to be degrading DCE at that location. And the key thing is, if you only measure TOC, well, TOC can't tell the difference between acetate and butyrate. I firmly believe sometimes measuring fatty acids is worth the money. To overcome the DCE stall, number one, you got to get better distribution. Injecting more fluid, both EVO and chase water. Make sure you don't have stagnation zones, and try to optimize your well spacing to save some bucks. And that's all I have. Thank you so much.
All right. Awesome. Thanks very much, Bob. That was a great presentation. Okay, yeah, so we got some questions and rolling in, and we've got a little bit of time here, so let's start off. So, Bob, going back to kind of your explanation about oil retention, and I think somewhere there you mentioned something about cumulative frequency, and so this question here is just, you want some clarification on that term, like what does that mean, and in relation to oil retention, how does that impact that process?
Oh, I'm sorry. I'm talking statistics. If you guys remember when you took statistics in college, they talked about a probability density function and a cumulative density function. Well, all this graph, when I say cumulative frequency, it's just, I forget how many data points are in this figure, but maybe 100 data points. And the lowest measured value of oil retention is over here, and then we plot them as they go up. And so this is the 1% of the data, 2% of the data, 5% of the data. And as you go up, and 100% of the data has an oil retention less than, what's that about? Oh, maybe 0.7 grams per gram. And that's all cumulative frequency is. It just percent of the oil retention values less than that number. And please text Brad if that didn't explain it.
Yeah. Okay, so the next question is, this is really kind of a two-part question, or sort of two questions in one, I guess. Okay, so what is going back to the mixing of EVO and kind of the sequence of injection? You recommend mixing all the EVO and water together first and injecting it, or injecting the EVO, I guess, by itself neat, and then following that with like the chase water? In your experience, what gives you the better distribution?
Okay, first of all, I would never inject EVO neat. It's too viscous. I mean, it's not super viscous, but it does have a higher viscosity. That's going to slow down your injection rates, because the higher the viscosity, the higher the back pressure. We typically dilute EVO maybe 4 or 5 to 1 with water. and then follow that with additional chase water. At least in the computer modeling simulations we've done, it doesn't make any difference whether you dilute 100% of the EOS with 100% of the water, and you just make a uniform distribution and constantly inject, or you make a more concentrated EOS solution, not 100%, but maybe a 4 or 5 to 1 dilution. So typically on average, people are ending up injecting maybe 1 part EOS to 10 or 20 parts water. I'm advocating injecting, diluting, taking about half the water, mixing it with the EOS, and injecting that sort of more concentrated EOS solution, and then taking the remainder half of the water and following that. Why do I do that? It really has nothing to do with oil distribution. What it does allow us to do is do the dirty operation during the day when the guys are around. They can inject the EOS during the day, clean out the piping and the hoses and flush out the drums and pack up. And then we'll inject just plain water at night. That allows me to inject more water at a very low cost. Since it's running at night and often we don't have anybody there, we'll inject at a low flow rate, but it costs very little to do that, and it's really a cost issue.
Right. Okay, so then the second question is, and I think I know the answer to this, so I'm gonna try to answer it, Bob, and then you can tell me how wrong I am. So the question is, you know, going back to the design tool kind of towards the end when you were looking at the well spacing and the cost relationship. So the design tool, and this is true of both the ESTCP design tool and then our EOS design tool that people use, both the web-based tool and then the one that I would use if somebody called. That looks at the total treatment area, you know, so you enter your X and Y and Z dimensions into the tool. And so, and it doesn't look at anything on a per well basis. So why does the number of wells change the amount of EVO required? And I think the answer to that question is that from one aspect that is true, that if you start with a fixed treatment area, you know, maybe your number of wells wouldn't change too much, being sure that you're injecting the right total volume. But in this sort of simulation that you did, in this data set that you presented, increasing well spacing increases ROI, and therefore it increases your treatment area. And so when you increase your treatment area, you would increase, you know, the amount of substrate and the amount of water needed. Is that, am I close to being right?
Dead on. And actually, if you're doing a source area treatment, well spacing should not affect the amount of oil. The specific case I was doing in that example was a barrier, and I'm trying to point it out. I don't have a great image here, but say this well spacing is 15 feet on center from here to here. Well, then the width of the barrier you'd imagine is maybe 15 or 20 feet. Well, at least the oil treated zone is 15 or 20 feet wide. If the spacing is 30 feet center to center, then the width of the barrier is probably going to be 30 or 40 feet wide. So in a barrier, when you double the well spacing, you essentially double the effective thickness of the barrier, and you double the amount of soil you're trying to treat with oil. But that's specifically for barriers, not necessarily for source area treatments.
Okay. Okay, so there's a bunch of questions about this. I mean, I think I'm counting like 4 or 5 questions from different individuals. When we're talking about doing these injections, obviously we're doing this from a biological standpoint. We're trying to influence microorganisms, and so and this has come up to me a lot from folks over, gosh, probably the last couple of years. And but the question revolves around conditioning the water prior to injection. So if you have a moderately reducing aquifer and you're going to use municipal water, or let's just take the context out. If you're using municipal water, period, for mixing and chase water, should you condition that water? Should you make it anoxic, or should you dechlorinate it, or both?
Okay, so let's separate out a couple. When you're injecting municipal tap water, it contains oxygen, it contains some chlorine, as well as it contains, well, I think that's the major things. Our experience is that when you inject oxygenated water into an aquifer that's got EVO, even if the EVO, I mean, the oxygen in that water will get essentially 100% consumed definitely within a day, probably within hours. And so the amount of oxygen in the water, at least for this initial injection, we don't think is important at all. I mean, we're injecting 10,000 times as much oil as you need to consume the oxygen. So the amount of oxygen you're adding is just really trivial. Now, there is an exception to that where people bioaugment, and people have shown that the helicocoides is sensitive to oxygen concentration. So if you're going to bioaugment at the exact same time that you're injecting, there is an argument for conditioning the water. I've seen people successfully do it other ways. We'll typically prepare anoxic water, and we'll sort of add bugs, and we'll chase it with a couple 100 gallons of anoxic water behind it. Now and then follow that by aerobic water, with the idea that we at least have a little cushion between those two. So if you're bioaugmenting, there's certainly an argument for trying to keep as little oxygen out as possible. Now, chlorine is a different issue. Again, if chlorine comes in contact with reduced aquifer material, iron and manganese and organic carbon, that chlorine will get consumed very quickly. But when you have chlorine in your tap water, there is also potential that you could have chloroform, which is a disinfection byproduct from water chlorination. Presumably, if you're injecting using tap water from municipal source, the amount of chloroform in that water that they're selling to people to drink every day, I would think should be okay to inject in your aquifer. But I won't go there, and I'm not a toxicologist or whatever. And there are some states and some localities that have concerns about, well, the drinking water standard for chloroform might be 100 micrograms per liter. Well, I don't know what the drinking water standard, I shouldn't say that is. But the drinking water standard for chloroform might be quite a bit higher than the groundwater standard for chloroform. So you need to look at that. And if the chloroform standard in your groundwater is higher than for tap water, then you may have to run it through activated carbon to get rid of the chloroform.
All right. And just as a quick follow-up to that, if somebody needed to prepare some anaerobic water, some conditioned water, there are a couple of methods to do that. Like you said, you could run it through a carbon filter. You could add a oxygen scavenger like ascorbic acid or sodium ascorbate, or you could do it with a biological method where if you have the time, you could prep a tank of water. You know, obviously it's closed off to the atmosphere. You could add some EOS or some other organic material to it, inoculate it with, you know, baker's yeast or dirt from the ground or something like that, and let it sit for a few days, and that'll make it go anaerobic. Are there any other methods that you know of, Bob, to make the water conditioned if somebody needs to do that or wants to do that?
I think those are the basic ones. The other thing is, you know, yeah, it's activated carbon, biologically remove it, or use some chemical oxygen scavenger.
Yeah, and I guess if you had the equipment, you could sparge it with like nitrogen or another noble gas or something like that. But
yeah, but that
may be,
tends to be incredibly inefficient. I mean,
well, I was going to say probably expensive, but
yeah, that would take a really long time. I would definitely argue for throw some EOS and some baker's yeast in a drum and let it cook for a day or two.
All right. We've run over our time, but it hasn't kicked us off yet. So I'm going to do one more question just because I think it's a pretty good one. Going back to the total dissolved solids and the retention and how that affects EVO distribution. Well, so this is the question. I'll just read it verbatim. You know, if we want better distribution and we don't want to lower retention, and if we want better distribution, don't we want lower retention and hence lower TDS? So why add base?
If your pH is neutral, don't. I mean, there's no reason to add base. But if the pH of your aquifer is 5.5 or 5.6 or even 6.0, you may have to add base. The key thing, the other is particularly if you have a relatively high contaminant concentration, when you convert TCE to ethene, you're releasing hydrochloric acid. If you've got high contaminant concentrations, I think I worked it out for every pound of PCEU degrade, you produce like 0.8 or 0.9 pounds of hydrochloric acid. So if you're burning up a lot of chlorinated solvent, you can produce a lot of acid and the pH can drop. If the pH drops, then all sorts of bad things happen. So no, if you've got a naturally neutral aquifer, you're probably fine. I will caution you though, my experience is most of the areas with naturally neutral to slightly alkaline aquifers are in more arid areas where the groundwater has already fairly high total dissolved solids. So in the east, the natural total dissolved solids is low, but you probably have to add base to neutralize the low pH. In the west or in arid areas, if you've got a naturally alkaline aquifer, you probably have moderately high total dissolved solids.
All right. Well, we're going to stop there because we're past time. Bob, again, I really appreciate your time. Excellent presentation. And I want to extend my appreciation to the audience for sticking through. We had a lot of people listening in to the Q&A session. A lot of people stuck around for that. So I want to appreciate great appreciation to everyone for your time. Thank you very much for attending. If you've got any follow-up questions that we didn't get to, or you think of something in the meantime, you can just email me or give us a call. I think everyone here has my contact. Or you could always just visit the website and contact us through there. Thank you, everyone, and have a great day.
Thanks a lot, Brad. Bye-bye.